Okay, so here is another proof of Bloch's theorem. So we now know that, well, we'll come to that. So what we are doing here is that we are expanding the electronic wave function in a periodic potential in terms of plane. That's the starting point. Plane waves form an orthonormal sort of basis set. So therefore, and we are using periodic boundary conditions, so we can normalize them. So so that's what we are doing. So these are the set of plane waves that satisfy this boundary condition that we just discussed. And then these electrons are moving in a periodic potential. So all that we are saying, what is the property of this? All that we are saying is that if you translate this or any integer multiple of A, you get the same potential. So therefore, the whole, of course, the Hamiltonian has this discrete translational symmetry, but more importantly for us here, U of R. So U has Fourier components only at the reciprocal lattice. So that we will write as this. This is something we discussed last time. We will assume few more things about U. Not assume, I mean, these are, some of them are always true. So this is a real potential. So therefore, U being real, so this is a consequence of the fact that U is a real potential. And then if yeah, it has inversion symmetry. So that is minus 1. Additionally, you can show that G will also be minus, which is of course star because of the fact that U is real. So these are some of the things that we will use, and we will use them in the Schrodinger equation for the electrons. Okay, so electrons experience potential U and they are non-interacting. So the Hamiltonian is just a single particle Hamiltonian. That's the Schrodinger equation. Now what we do is we use this expansion over there. So that is and here we use So I'll take this term. So this with this and this term I'll take to the left. And so with that, I can write this as then I have this term, which is well, that was a plus. Actually, what I want to do is I want to take this e to the 5k dot r's of study. So I have this here. And then, what is it? So, what I would like to do here is, yeah, no, before that, one second. I'm summing over all g's here. So let me write g plus k, this g plus k over here is equal to some e prime, right? So then I'll have an e to the I k prime dot r, and this g would become here, g would then be I'm missing something. So there is a k over. So k becomes k prime minus. So this subscript here becomes k prime minus g, and this thing I'm calling k prime. Now, if k is summed over, since g is summed over, k is also summed over. It's the same thing as saying that I'm summing over k prime, so there is no reason for me to carry a separate index k prime. I can just call it k. So with all of that, I can write that term as. So this will become c k minus g, and then this becomes e to the I k prime dot r, but then I'm summing over k, so I can call that same thing, e to the I k dot r. So it's just a manipulation of the indices. There's nothing more to it. Okay, now what we have here is that these are plane waves.
Sir, I did not get the last line.
You mean the
how you arrived at the last line from the
how the manipulation is done?
Yeah.
Okay, so what you do here is you call k g plus k as k prime. So this k becomes k prime minus g. Okay, and so then this term, I'm writing it separately. This would have been sum over g, ug, c, k would be k prime minus G times e to the I k prime dot R, right? But then see here, I'm summing over G, and I'm also summing over K, which means I'm summing over K prime, and all possible, I'm summing over all possible Ks. So I'm summing over all possible K primes. So therefore, I can, instead of calling it K prime, I can call it K, and I can write.
Okay.
So you're assuming that G and K have same periodicity.
Yeah, because some
then-
Ks are Gs, so Gs are sort of a subset of the Ks.
But then what we are proving?
Sorry.
We had to prove that psi of R is periodic.
No, that is not what we are proving.
Sorry. Psi of R is some phase factor time a periodic function.
Yes.
So are we not implicitly assuming that when we are saying that K is lying in the periodic, like K
No,
is having the same periodicity as
no. We are saying Ks are periodic with the periodicity of N1, A1, N2, A2, A3, A3. They don't have the periodicity of the lattice. They are not periodic with A1, A2, A3. Over this big box, they are periodic, yes, because we are applying periodic boundary conditions. Okay, so then the next argument is that we have so these are plane waves. These are orthogonal, different for different Ks. So what we have to have is that all these coefficients for all Ks, they have to vanish. Okay, so we have so I mean you may have already noticed that what we are trying to do is to sort of pass the original Schrodinger equation written on the top, the right. This is the differential equation, of course, in the K space, which would give us some algebraic equations involving the coefficients Ck. So that's the sort of goal, but that will teach us something more. I mean, a lot more. So this equation, I can write for each K such an equation, and we already saw what are the allowed K values. But what we can do is we can this K can be anywhere in the reciprocal space. So what we want to do is if this K is not in the first Brillouin zone. Now again, you have to have your idea of Brillouin zone very clear. You have a reciprocal lattice corresponding to the direct lattice, and the Wigner's times primitive cell of the reciprocal lattice is your first Brillouin zone. Okay. So if K is not in the first Brillouin zone, let us write. How do I write it? So if not in the first Brillouin zone, then write but Q is in the first version. Okay. So now let us write this in terms of Q. So then this equation becomes and this. So now again some manipulation of indices is involved. So let me try to give you the idea what we are doing here. The first thing we do is that okay, so we could just okay, I'll not do that. So suppose now I'm writing G double bracket as minus G. So then I find C minus. Okay, so that's what you get if you use this. So this thing is equal to 0. There was a sum over G, which I can write as a sum over G prime. I'm summing over all G's, and each of these G's are translated by this amount G prime. G prime is a fixed quantity, fixed vector. So therefore, a sum over G can be replaced by sum over G double prime, and things come to this form. But then there is, I just change the notations again. It's just a matter of convenience. So I can again write things in terms of. So I'm replacing Q by the notation K. It's just a change of notation. This K is in the first version. I'm replacing G prime by G. So don't get confused by this change of notation. There's nothing fundamental about it. Plus G prime. So finally, you can write it in this form. So just sit down and just see how the manipulations are done. As I said, there's nothing sort of terribly insightful here. But what is important is this relation. Sorry, this is not Q. I wrote K here, so we have K here. And this K was the same as this Q. So this is in the first Bernoulli. Now, it's more important to sort of understand the implication of this equation. So what I can do is, first of all, you see that this C. So this is an equation for CK minus G here. CK minus G prime. So if I choose a K, if I choose a particular K in the first Brillouin zone, then what will the CKs or CK minus Gs that will appear in this kind of equations? So when G is 0, of course, there is a CK. When I have the next G, let me call that let me call that G1. So it will involve CK minus G1, and then it will involve CK minus G2, and so on and so forth. So if I want to sort of evaluate this quantity, if I wanted to calculate this coefficient, it is coupled through this sort of equations with these coefficients, K minus G1, K minus G2, and so on. It is not coupled to any coefficient of the type CK prime, where K prime is also in the first. It is not. So this CK and CK prime are not appearing in this kind of equations together. So what that, and if K is in the first Brillouin zone, K minus G1, K minus G2, none of these are in the first Brillouin zone. They cannot be. If you translate it by the reciprocal lattice vector, you go out of the first. So you have broken down the equation, this kind of an equation, into a number of equations, one each sort of. So these coefficients, I mean, like you could solve it separately for each K point in the first Brillouin. So that is one thing you have done. And then for each of those K points, the equation or equations involve CK minus G1, CK minus G2, etc. All all G vectors that you can have. So these are a set of coupled algebraic equations involving these coefficients. For a different K point in the first Brillouin zone, you have another set of coupled algebraic equations and so on. So you basically have to solve those equations to get these coefficients. But two different K points in the first Brillouin zone, their coefficients are not coupled. Okay. So if you understand that, and now you also understand why this index K comes. So I'm solving the this equation at a particular K point. So I can label that by the K point in the first Brillouin zone as psi K. So I'm solving for psi K of R. And because only these coefficients are coupled, I can write this as, so the general form of the solution will be this. So this form of the equations tell me that I can write the general solution of this in this form. So let's see, then I can write this as and this is conventionally written as UKR. So this factor naturally appears in this form. So now you see, if you write CR plus R, because of this particular form, so this has a e to the I g dot R form. So in case of I, if you write R plus R, this e to the I g dot capital R will give you 1. So this thing does not change. What changes is this part. So you will have because UK is periodic with periodicity of the lattice vectors. So the general form of these states, electronic states, is some e to the I k dot R times a function which is periodic with the lattice periodicity. But this whole thing is not lattice periodic. It picks up a phase like this when we translate it. Okay. Any questions?
Sir, sir, in the second form, we saw that the coefficient Ck, the case which differ only by reciprocal lattice vector, those are coupled in an equation.
Right.
So, so can this form be derived from the first proof?
No, I don't think so, because the first proof does not assume that they are, some sort of linear combination of plane waves. There is no concept of plane waves in that.
Okay. No, actually, I was thinking that in the two proofs, we use the same kind of, same kind of information that the wave. What should I say? Okay, I will frame the question later and see.
Yeah. You think about it, frame the question more clearly, and then we can discuss. All right. So now this form is actually very insight. Gives you a lot of insight, which are absolutely crucial in understanding electronic properties of solids, as I already said. So let us go through them one by one. Yeah, before I go to that, let me ask particularly, this question is for the MSc students. So how do you think you are doing with the first assignment? In the sense that, do you think you will be able to submit it next Monday, or would you, like to have a little more time? Any opinion?
Sir, we will inform you by the next class. Most of us are working on the assignment and facing some problems. Mostly with the programming.
Yes, I understand that, and that's why I don't want to sort of push you and say that no, you have to submit it on the 6th. What I want to you is that if you want a little more time, that's also fine with me. But I want you to sort of spend some time on it and do it properly, so that you get a good understanding and good feel of it. Okay, so you let me know. But the second one, you have to, so that's a more conventional thing. So you should submit this. Okay, now the first point that I want to make, and which is sort of obvious looking at this particular form, is this form, whichever way you look at it, because this is a combination of plane waves. So therefore, these wave functions are not momentum eigenstates. So although we label these states by a k, h cross k is not in this state. And that becomes, I mean, as I said, these are linear combination of plane waves. Also, if you just apply the momentum operator, you can easily see that it's not a state. Yet, for reasons that hopefully we at least partly will discuss in some subsequent lecture, is that K is or H cross K is crystal momentum. Yeah, so maybe it'll become clear later. Now this K is so this K and this the first Brillouin zone. Why is that? So look at this form. So suppose K is not in the first Brillouin zone. So K is not in the first Brillouin zone. I can write some K prime. Like this, where one is in the first bit. So then, let us see. So, and so I'm writing K as what am I writing? K as K prime minus. Okay, so this has to be some different G. So let us call that G prime. Okay. This is G. So I can pull this in. Okay, now the point is that what happens if I translate it by so that is the whole point. So that gave me that index key, right? So if I translate it by R, I will of course get some e to the I k dot capital R here, but then there is also a G prime sitting here. So so I'll get a G prime dot capital R here and a G prime dot R here. So the G prime dot capital R can be pulled out here. So eventually the factor I'll get in the front will be like e to the I k prime minus G prime dot R. Now it is true that this is 1, but then when I write it in this particular form, this is just E, right? From my definition. So the factor that I pick up can also be viewed as just K dot R. So basically, whether K is in the first Brillouin zone or or not, I'll pick up the same factor. And yeah, so that's the point. So therefore, I can always confine this to the first Brillouin zone. The most important point here is that. So let us see what is the sort of what is the eigenvalue equation that I get. Remember that U is a periodic function. U is a lattice periodic. So U P R plus R is U P R. So it's a lattice periodic function. So therefore, now I apply the Hamiltonian on this wave function, which is E. And what is H? H is this is also lattice period. So this is my Hamiltonian, and which acts on this function. So now what you can do is you can sort of act this on these two parts and so on. I'm not going to do the algebra here. So if you work, so consider this wave function to be a product of two functions, and you have these two terms in the Hamiltonian, then you work through it. So basically, what you will end up getting is sort of an eigenvalue equation for the U case, so of this particular form. So H. So HK is different from this H. Okay? HK is something that acts on UK. I'll write the form, the final form that we will get. So this will be of the form. So that's the kind of an equation, eigenvalue equation that you will get with the boundary condition. What I wrote there at the top. So what is this? This is now notice this. This is a Hermitian operator. This is just some real vector K. This is like the momentum operator. This is a real potential. So this whole object. So this is my HK. The K index comes from this. So this operator is a Hermitian operator. Acting on UK gives me this kind of an eigenvalue equation. And these are just the eigenvalues, the energy eigenvalues of the state psi k with the full Hamiltonian of the lattice. So this is a Hermitian eigenvalue problem confined to a finite region because of this periodic boundary condition. So this is similar to a sort of a particle in a box problem or free particle in a finite box problem, in the sense that you are applying periodic boundary condition. That's sort of a problem. And the general features of such kind of eigenvalue problems is that you get an infinite set of discrete eigenvalues in general. So for each k, now this is the important point, for each k, you will get an infinite number of eigenvalues. So I get an infinite number of eigenvalues for each k, and on very general grounds, I will see that k appears as some sort of a parameter here in this Hamiltonian. Hk depends on this parameter k, and is, generally I can assume these these eigenvalues to change continuously as k changes. So for small changes in k, there's no reason why epsilon k should change discontinuously. So I can expect the sort of psi k's and epsilon k's in particular to be continuous functions of k. We have already seen what sort of functions psi k's are, but we expect epsilon k's to be continuous functions of k. So these are the two things. So epsilon k's are assumed to be continuous functions of the parameter k, and for each k in the first Brillouin zone or each k anywhere in the reciprocal space, I get an infinite number of these eigenvalues. What more? Number of then what is the next? Okay, so this is some psi k primed. K prime could be anywhere in the reciprocal space, and I write K prime as I'm doing something similar to the discussion earlier, but because while K is so now I substitute. So this is sign here. But then sum over all g's and sum over all g plus g primes are the same thing. Because we have essentially infinite number of g's. So sum over g and sum over g plus g prime are going to be the same thing. So so then this part remains k of r. So that is what we get, which is same as r. While k is in the first inversion. So k psi k prime is same as psi k when k and k prime differ by reciprocal lattice vector. In other words, psi's are periodic functions in the reciprocal space with the periodicity of the reciprocal lattice. Again, keep in mind, psi's are not lattice periodic in the real space, but they are periodic in the reciprocal lattice with the periodicity of the reciprocal lattice. So if you change k by k plus g, k to some k plus g, any g, you get the same wave function. Therefore, you get the same same energy. So therefore, psi. Okay, and this is where the index n comes from, because you have infinite number of solutions. I'll make the meaning of n clearer as we go along. So these are also very, very important ideas, that your electronic wave function and consequently the energies are periodic functions in the reciprocal space. And because these are periodic functions, okay, before that. So how do I now, what is this n? So let us come to this business of n. So at each k point, I have infinite number of solutions, infinite number of epsilon n's, let us say. And as I change k slightly, the energy changes slightly. It's a continuous function. So I label my states such that for a given n, this condition is satisfied. Okay. So I may be at the origin of the reciprocal space. Let's say I have some energy which is the lowest. I call that, let's say, the first energy state, n equal to 1, let us say. Then as I change k, this energy evolves, this energy changes. And when k changes enough, let's say by a reciprocal lattice vector, it comes back to the same value. So then I follow this change of epsilon as a function of k, and at each k, the corresponding state and the energy, these are labeled by n equal to 1. So that is my n equal to 1 state. Similarly, I'll have n equal to 2, n equal to 3, etc., etc., and infinite number. So these, yeah, was there a question? Okay, so for each n, this set of levels in the sense that one level at each k. For a given n, this set of levels that constitute this periodic function epsilon in k is called a band. That forms a band. So for a given value of k, I have one band. For another value of k, n, I have another band. So for a given value of n, I have a band. For given another value of n, I'll have another band, and so on. So these are band energies, and these are band states. Remember, these energies are functions of three coordinates: kx, ky, kz, or whatever way. So k is for a three-dimensional solid, k is space is three-dimensional. So it's a function of three coordinates in k space. So having this mental picture for epsilons, these bands, is very, very important. I repeat that I designate an energy state with an n such that as I vary k, this energy changes, but when I move by a reciprocal lattice vector, the value comes back to the same. So there is variation of this function epsilon such that epsilon k plus g becomes equal to epsilon k. This function is called a band. This set of energies constitute a band. So now let us try to see some real bands. Okay, so if one is talking about three-dimensional solids, it's very difficult to sort of visualize bands because there's no way we can plot something which is a function of three variables onto a 2D surface. That visualization is difficult. But more easily we can visualize if my actual system is two-dimensional. So that's what I'll sort of start with to give you a feel of how things look like. And once you see it in two-dimensional case, it's easier to sort of visualize it, at least mentally, for three-dimensional space. So graphene is a known system. It's a layer of carbon atoms. And so it's a two-dimensional lattice. So its Brillouin zone is also two-dimensional. K space is two-dimensional. So energies would be surfaces in that space, okay? Which one can at least attempt to visualize. So let us try to do that. Okay, so if you see this here, this one, let's see if we can bring up a bigger picture. So can you see this screen? So graphene is a hexagonal lattice. And if you work it out, the Brillouin zone also happens to be hexagonal. So the hexagon that is drawn there is the sort of the first Brillouin zone of the hexagonal real space lattice, or rather a honeycomb real space lattice. And in this sort of box type of thing, what you see here are sort of two surfaces you see, one below, one above. So this is the surface of, this is sort of two bands, okay? Now bands in this case, because I have a two-dimensional system, bands are a function of kx and ky. So those are the axes marked there. Akx, A is the lattice constant, Akx and Aky, and the third direction gives you the energy. So you see how energy varies as a function of kx and ky. So these are two bands. So that's how things would look in two dimensions. And so obviously you can't visualize in this fashion if you have a three-dimensional system, obviously. But you get the idea that in three-dimensional solids, energies would be function of kx and ky and kz. and would have similar sort of hypersurfaces in higher dimensions as your bands. Is that idea clear? If anyone has a confusion, please ask at this point. All right, so this band structure, which is just a simple consequence of the fact that electrons are experiencing periodic potential. There's sort of nothing more to it. It's just the periodic potential that ensures that you have these bands. But that already allows us to understand why some materials are metals, they conduct electricity, while some others do not, and so on. So there could be a class of materials where, let's say, a certain number of bands are completely filled and the rest are completely empty, depending on how many electrons you have in the system. So those kind of situations where the filled bands are separated from the empty bands by regions in energy where there are no electronic states. These are semiconductors or insulators. And then there could be other class of systems where one or more of these bands are partially filled, and those are the metals. And as we'll see later on, that when you have partially filled bands, applying an external electric field, for example, drives these electrons. So you can have a current in such systems. On the other hand, if bands are completely filled because of this periodic nature of these wave function, electron wave functions, you cannot drive the current. So there's no net current if the bands are completely filled. So we understand the difference between metals and insulators in terms of this band picture. Also, if you have a metal, then one or more bands would be partially filled, as I said. So, but then states up to a certain energy will be completely filled. I'm talking of zero temperature. States up to a certain energy will be completely filled, irrespective of what the shape of your bands are, and the rest of the states will be empty. So if I draw this surface, which is the sort of energy surface of the highest occupied energy level, that will cut different bands in different ways, and the collection of all these. So in general, they would give me surfaces. Okay, if I draw the constant energy surface corresponding to the highest occupied state, that will have intersections with various bands. It can have intersections with more than one bands. And so each of these intersections will give me some surface. So the collection of all these surfaces is called the Fermi surface. So the idea of Fermi surface remains the same. It's the surface corresponding to the highest occupied energy level. But in the Sommerfeld model, in the free electron model, this Fermi surface was just a sphere because the relation between epsilon and k was simply epsilon going as k squared. For these kind of periodic solids, depending on what sort of structure you have, etc., etc., the shapes of the bands, the relation between epsilon and k need not be k squared. Could be different. So depending on that, the Fermi surface need not be spherical. It need not even be. It need not even consist of a single sort of surface. It could be a collection of surfaces. So some of these details we'll see later. I mean, just the words will not convey anything. But just to give you an idea that even in band picture, when you have metals, you have this idea of Fermi surface, except that the Fermi surface, the shape of the Fermi surface would be more complex in general than a free electron spherical Fermi surface. Yes. So do we have any questions at this point? Okay, if not, there's something more that I wanted to talk about. So let us do that. Okay. Maybe one more thing I can talk about before I move on. Yeah, so let us look at this picture that is sort of enlarged here. So you see some lines are drawn, some points are marked gamma, K, N, etc. So typical band structures are drawn like this. I'll show you when we discuss the next chapter. But what do they mean? So, as I said, when but this is particularly true of when one draws band structure for three-dimensional solids. There is no way we can visualize a function of three variables, as I said. So, what one does is one chooses specific directions in the Brillouin zone and plots how the band energies change along those directions. So this is again for the graphene example that I was talking about. So, if I want to visualize this as a surface, this is the figure on the left is what I just showed you earlier. But then the Brillouin zone, as I say, I'll turn on the camera.
Sir, are you writing something on the board?
Yeah, I'll turn on the camera. I know the camera is off. Yeah. Okay. So that is the Brillouin zone, which you just saw, and here these points are marked like this is typically marked as gamma or gamma bar, and this these K and K prime points are at the corners of the hexagon. The name is in the middle of one of these sides. So what you just saw a while ago are the variation. Let me bring that up once again. Yeah, the figure on the right. So that you see gamma, K, M, gamma, and so on. So these are, so what these plots show is how the band energies change as you go from gamma to K, K to M, M from M back to gamma, and so on. So this is how typical band structures are drawn. And this is the way, only way you can draw band structures of 3D solids. So one of these lines, if you look at the bottom line, for example, something is equal to minus 20 EV at gamma equal to 0. So if we call that as my first band, then as you change K from gamma towards K, you see how the band energies changes. So that is that epsilon 1 as a function of K and so on. Okay, that is how typical band structures look like. And we just discussed the formal theory where it comes from. It's all a consequence of, let me repeat once again, because this is very, very important. It's all a consequence of periodic nature of the potentials that electrons experience. Okay, so then the last bit in this part. So as we discussed in the sum of a model, one may require to calculate quantities which this Q is not not a reciprocal, not a vector in the reciprocal space. This is some quantity Q for quantity. One may require to calculate such quantities. Q is 1 over P, that is great. In case of, so I'll already put a factor of 2 here. This doesn't include spin. This 2 comes because of the spin. So exactly as we did in case of the sum of the model, because the sort of volume in K space per allowed K point is the same in both cases, so we can replace such summations by integrals. So this would be so this n is the band index. So there's a quantity Q, function of K, which can have different contributions from different bands. So that is that band index n, and the K sum is replaced by this integral. Now, as we saw in that case, there are situations where the only K dependence of Q is through the energy epsilon. So if that is the case, if Q depends on Q, yeah, then I can bring in this idea of density of states. Where G of epsilon is the density of states, is the sum over density of states contributed by all the bands. So it's this sum over the density of states coming from each band. And what is the how do I define the density of states? So it's sum over K points, but then I replace that by integral. This 2 is for the speed, and if there is a state with energy epsilon, then I pick up a contribution. So that's the definition of density of states. And this integral is over the first Green zone. Okay, so what is this? What was this idea of density? So density of states, this is again because this times the number of allowed points in the and so this is the idea of density of states. It's the number of key points in the nth band such that their energies are between epsilon and epsilon plus g epsilon, that is g epsilon g epsilon. Now, what is the number of allowed key points in the nth band with this energy? It is the volume of it is sort of the volume of the reciprocal space in this region divided by the volume per k space in the reciprocal space. So it is the volume of reciprocal space between these energies divided by the divided by the volume per k point in the reciprocal space. So if I do that, then I can write this. So what is the volume per allowed key point in the reciprocal space? That was delta K, which we have this. So if we divide this object by that, and we have to write somehow the volume of in the k space so that energy is between this. So then I can write there is an N. So if the energy of the nth band happens to fall in this region, I pick up a contribution 1, otherwise it is 0. So that is that. So basically then what I have to calculate is the volume in k space for this. So this is done in the following way that I consider two energy surfaces. Okay. Or what I would call energy isosurfaces. Epsilon and epsilon. And then if delta k is a vector, remember these are surfaces in the k space, and if delta k is a vector perpendicular to this surface, let's say at epsilon 2 up to the surface at epsilon plus d epsilon, then this can be written as so this volume integral in the k space now I'm replacing by integral over the surface times this thing delta k. But delta k is the vector from this surface to that surface, and this is a sort of elemental surface on this isosurface, this energy isosurface in the k space. Okay, so what does that? How does that help us? So first thing is to we have to evaluate what delta k is. Okay, so how do we calculate delta k? So remember these are two isosurfaces. So I don't know how to draw it because it's sort of difficult. I'll try to show you later some figure from the book. So basically, what I'm saying is that epsilon plus d epsilon is CB. Or this way or this way. So what this means is that this delta k moves from the epsilon surface to the epsilon plus d epsilon surface. So if I have two surfaces like this corresponds to epsilon, this corresponds to epsilon plus d epsilon. Then delta k is this way. This two. So epsilon plus d epsilon is obviously this. So from this, what I have is the same thing. Okay, so don't get confused. So delta T. Remember, this is a key space sort of gradient of epsilon A. So then we'll just plug this over here. So eventually, what we get is, and this is the important thing. So that form is the important thing. Now notice what we learned from here is that whenever the gradient vanishes, that denominator becomes 0. So what does that lead to? Now, what does that lead to? Of course, depends on which dimensions you are in. but it definitely leads to some large value in the density of states. Turns out that if you are in 3D, you will have a sort of density of states that increases like root over epsilon. On the other hand, if you are in 2D, that will give you a logarithmic divergence in the density of states. So maybe I'll ask you to work these out as exercise. But the point is that whenever this quantity, the k-space gradient of the band energy becomes 0, you have a diverging, you don't have a real divergence in 3D, but anyway, you have large density of states. So, and that has physical consequences. So this particular situation is called the Van Hook singularity. And it has observable consequences. I'll show you in a minute. And remember that a few minutes ago we discussed that epsilon and k's are periodic functions. These are periodic functions, so therefore they have maxima and minima. So as you go over the entire reciprocal space, there are maxima and minima of epsilon k. So therefore there will be points, there will be regions where this epsilon grad of epsilon k would vanish. So you'll have these things, these sort of Van Hook singularity. So what happens if you have a Van Hook singularity? Then of course, if you have a large density of states, suppose you have a situation where you have the semiconductor. So some set of bands are completely filled. There are other set of bands that are completely empty. But then in the density of states in those bands, suppose you have such a singularity. So there are a large number of states that are available there. So density of states, remember, is the number of states in the energy range epsilon to epsilon plus d epsilon per unit volume. So apart from that volume part, it's the number of electronic states available in a certain energy range, epsilon to epsilon plus d epsilon. So when there are a large number of states available, a large number of electrons can go there. So suppose then you are supplying energy to that material in the form of maybe photons, which have just the right energy. So the material would start sort of absorbing energy, and electrons will be excited from the lower energy states to the higher energy state. But then there are a large number of states available there, so a large number of electrons can get excited there. So there will be a large absorption of the incoming photons or the electromagnetic waves, whichever way you look at it. So the absorption coefficient in that energy range would show a certain spike or a spike with some characteristic energy dependence, etc. So these have observable consequences. It's not just the electronic density of states. When you study phonons, let me see if we can get there. Phonons also have bands, and if they have similar structure, you can also have band of singularities in the phonon density of states. So, okay, so let us try to see if I can show at least some of these things. Yeah. So this is a plot. So don't worry about so much about the details. Let me just tell you what is being shown here. The two plots show you the same thing. Basically, it's the absorption coefficient. Alpha is the absorption coefficient multiplied by the photon energy, and the x-axis is the photon energy cross omega. So as you see, this is for a material, indium arsenide. It's semiconductor material. Then below certain threshold, there is no absorption. Then as you cross that threshold, you go up in photon energy, H cross omega, and this, suddenly there's a lot of absorption, and it increases in a certain fashion. So that is, as I said, is the square root of omega, because this density of states goes in 3D, as I said, go as root over epsilon. So that maybe you can work out, as I said. So this is an observable consequence of a Van Hoff singularity in the density of states of the material indium arsenide. So just to show you an example. And let me see if I can show you the other thing.
How to withdraw profit from a limp trade without any commission? To make it a possible.
Yeah, so this is the picture that I wanted to show you. So you have these two isosurfaces, energy isosurfaces at epsilon and epsilon plus d epsilon, and then that delta k that I drew there, the vector delta k, is a vector along the gradient from epsilon to epsilon plus d epsilon. And using this picture, you turn this volume integral in k space into a surface times surface integral times delta k, and from that you get this expression which tells you that there can be these singularities. All right, so I think I'll stop here. So if you have questions, you can ask me at this point.